Okay, here's the backside of section 5.5. We're going to do the second half, and we're going to start out with logarithmic differentiation, which is something we learned already. This is used whenever the base and the exponent are both x's. For example, we had earlier problems where maybe the base was an x, but the exponent was not. It was just a number. Well, that'd be easy enough. You just go back to chapter 2, use the power rule, and you get the derivative to be 8x to the 7th. Now, of course, you could have it flip-flopped. You could have the base being a number and the exponent being the variable. In that case, we'd be on the section that we're on. It would just be itself, 8 to the x times natural log of 8. Of course, you would simplify the 8s. But if you have something like this, where the base and the exponent both have variables in them, that's a completely different story. Then you have to use logarithmic differentiation. So we're about to take the natural log of both sides. The reason that we want to take the natural log of both sides is, again, the 8x minus 5 needs to come down. And how do you get it to come down? We use the power law. The 8x minus 5 just drops down, just like, somebody's cat falling out of a tree. Hits the ground. Safely, of course. And now we have this. All right, now we're ready to take some derivatives. Of course, notice that the right-hand side, you have two things multiplied together, and both of them have x's, so you're going to have to use product rule. U prime v plus uv prime. Okay, I gave myself a little bit more workspace, and here we go. The left side, the derivative of a natural log of y is 1 over y. Oop, that's the wrong letter. dy dx. Implicit differentiation. On the right-hand side, you're going to have u prime v, that'll be 8 ln x, plus u v prime, which will be 8x minus 5 over x, because that's times 1 over x. All right, let's multiply both sides by y, because we want to get the dy dx by itself, like we have there in purple. Remember, the y actually was x to the 8x minus 5, and you have to replace that and put it back. Again, you want all x's in your answer, just in case you have to type it into the calculator. You don't want x's and y's together. All right, back up top, and we'll finish the next one off the same way. Okay, number 11. Again, we have some trig. I do like the fact that we have number 10 to look off of as a model. So again, we have x's in both the base and the exponent, so we have to use logarithmic differentiation. So hit both sides with a natural log. The exponent, the sine of 3x, can come down to ground level as a coefficient using the power law, which is going to set up a product rule situation. And implicit differentiation on the left-hand side. So once again, the derivative of natural log of y is 1 over y. Oop, wrong letter, dy dx. On the right-hand side, you have u prime v plus uv prime. There's the u prime v. I'm out of room, so I'm going to scroll and give myself some more space here. Okay, so we've got u prime v plus uv prime. There, that's better. Okay, we want dy dx to be by itself, so we multiply both sides by y, just like we did in number 10. But remember, from the original problem, y was equal to x to the sine of 3x power. So we'll just put that in and call it good. And that's both number 10 and 11. All right, now we're going to turn around and integrate. Now think about it. If the derivative of a to the x is itself times natural log of a, it's not too surprising that the integral of a to the x would be itself divided by natural log of a, plus c, of course, at the end. And so that's what we're going to do. All right, so let's start off with number 12. 16 to the x, so its integral will be itself divided by natural log of 16 plus c. Of course, remember that 16 is actually 4 squared, so you could go 4 to the 2x. You know what, even better yet, 16 is 2 to the 4th. And that would be a little bit more simplified because you'd have a smaller base and you'd have a smaller argument. So I'm going to make the 16 a 2 to the 4th, so that'll be 2 to the 4x over the natural log of 2 to the 4th. Again, I used the power law, brought that 4 down. Again, you cannot cancel the 4s. You can't cancel the 4 into the 2. You can't cancel the 2s. Nothing cancels. Okay, it just is what it is. Plus C. All right, number 13. 13 is actually 2 separate problems here. The first part, just up by a power, divide by the new power. So that's going to be 4/6 x to the 6th, which will become 2/3 x to the 6th eventually. And then we have the second part. Remember, I can split integrals and do them one at a time. And when you integrate the second part, it's going to be itself. But we have to be careful. So far in these other examples, we've only had a few of them, we just had it to the x power. But we have a danger of chain rules. Now, of course, there aren't any chain rules when you integrate, but there are u subs, which are the opposite of chain rules. So I want to make a u sub here in number 13. I want to call u the 2x plus 1. Better safe than sorry. Du will become 2 dx. I need a 2 dx. So I'll multiply by 2 here on the dx. I'll divide by 2. I'll put a 1/2 out front. Not way out front, but just out in front of the second one. What that does is that becomes a du. We now have 3 to the u being integrated with a 1/2. The green part's already finished. I mean, yeah, that's obviously 2/3. I can simplify. But now the integral of 3 to the u will be itself. It'll be 3 to the u divided by natural log of 3. And of course the 1/2 gets tacked on. Which sets up my final answer right here. Okay, just a couple more to go. Here's number 14. Again, you can see quite the spectacle. I do see 1 minus sine squared, which again, I'm like, that's cosine squared. I recognize that from the golden sheet. At this point, clearly we're going to need a u sub. We want to make it so that it's 12 to the u. So we want the u to be tangent of x. And then, of course, du, the derivative of tangent, would be secant squared. Let me give myself a little bit more room here. There, that's better. And that's simply going to become the integral of 12 to the u du, because we have a secant squared. It's 1 over cosine squared. And again, the beauty of the u sub is that a problem that looked pretty terrible when we first started now looks super easy. The integral of 12 to the u du is simply itself 12 to the u divided by natural log of 12 plus c. And when I say 12 to the u, remember that u has to be replaced with tangent of x. So there it is. Hopefully this is getting a little bit easier. One more problem. Number 15 is our last one in section 5.5. Okay, on this final problem, it's a definite integral. We're taking the integral from -1 to 2 of 3 to the 2x dx. Again, this is going to call for a u sub. I want it to turn out to be 3 to the u, so u will have to be 2x. Du then would be 2 dx. So I'll need to put a 2 on the dx, of course. And to make up for it, a 1/2 out front. Now I've got my du. I've got my 3 to the u. I'm ready to integrate. And the integral of 3 to the u du is itself divided by natural log of 3. Now notice what I did with the 1/2. I just kind of stuck the 2 back in. The 1 is invisible up top. All right, so we can do it like that if we want to. To be honest, I prefer to stick it outside. In fact, you know what? I'm going to do that. Okay, so you can see what I did. I just took the 1 over 2ln3, put it out front, and then the rest of it will just be 3 to the 2x, which will be a lot easier. In went the 2 and the negative 1. You can see that I got a 4 and a negative 2 as my exponents. Now I just have to figure out what that is. 3 to the 4th is 81 minus 3 to the negative 2nd would be 1/9 because that would be 1 over 3 squared. So 81 minus 1/9. Let's make some more room for ourselves. There, that's better. Okay, so as I said, we get the 81 minus 1/9. We have to simplify that up. 81 is 729 over 9, so take away the 1/9, you get 728 over 9. And you can simplify that down to the final answer of 364 over 9 ln 3. Again, the 728 and the 2 are both even numbers. They can be reduced. And there you have it. All right, that's the end of section 5.5. 2 more lessons to go in chapter 5, and we'll be all done. Nice job, everybody. I hope you enjoyed today's lesson, and I will see you soon.